Hey guys, this is Mrs. Coleman. In this video, we are going to talk about some alternate methods for calculating the enthalpy of a reaction. You'll remember from our previous labs and classes that to calculate delta H for a reaction, we could use calorimetry. So we can actually go into a lab and conduct the experiment and get temperature changes and use, delta H equals Cm delta T and calculate our enthalpy changes. And then, determine the enthalpy change for a mole of our reactant. Or the other one we did is we used Hess's law, where we were given a bunch of equations and we rearranged them so that they equaled the equation that we were trying to get to, and then we used the enthalpy changes for the rearranged equations and added them together to get a delta H of reaction or a heat of a reaction. So you can measure it or you can use known equations to get your enthalpy change. So today we're going to talk about two other methods for calculating the enthalpy of a reaction. So these are using standard enthalpies of formation to get your enthalpy of reaction, or you can use bond energies to get your enthalpy of reaction. So we'll start with the first one. Before I get too far, I want to point a few things out before I get into how to do this. So the first thing I want to point out is this little naught right here. So that little 0, that means naught. So N-A-U-G-H-T. And what that really means, when I see that, it means at standard conditions. And for reactions in aqueous solution, which we've been dealing with, we're talking 25 degrees Celsius, and we're talking 1 molar concentrations. And if we're talking about gases, we're talking about 25 degrees Celsius, and the pressure is going to be 1 atmosphere of pressure. So the trick to using enthalpies of formation, or standard enthalpies of formation, to make our calculations is you need to understand that this is only going to give you an enthalpy for your reaction or a heat content for your reaction if it's conducted at standard conditions. So the numbers that we're about to use only stand or apply at standard conditions. So if this reaction is not taking place in standard conditions, you cannot use the standard enthalpies of formation to calculate its enthalpy of reaction. All right, so to do this, you're going to need a table with standard enthalpies of formation for a whole bunch of different compounds. And what these is the heat content involved in the assembly or the making of these different compounds from their elements. So, for example, if I was just to pick one of these, let's say I was picking chromium, Cr2O3, notice it says solid next to it. It's because its formation as a liquid is going to be a slightly different number. What I'm really looking at is how that was made from the elements. So from solid chromium and from O2 gas. So how that amount of energy to take chromium solid and oxygen gas to produce Cr2O3, well, in standard conditions, the delta H of that would be negative 1139.7, as is evidenced by what you have in the table. So you need to understand that these numbers that are given in this table are not numbers for creating chromium, like for example, chromium oxide solid from anything other than its elements. All right, so let's do an example of how we would use this particular table to make a calculation for the enthalpy of a reaction. All right, so I've given you this equation, which is the combustion of methane, and I want you to calculate the delta H for this reaction at standard conditions using these heats of formation from this table. All right, and so to do this, you're going to need this fun-looking equation. This equation looks super scary when you first look at it, but it's actually a pretty easy equation to understand. So if I'm going to calculate the enthalpy of this entire reaction, what I'm going to do is I'm going to sum up. So that little sigma means the sum of. So I'm going to sum up the delta H of formation of my products, and I'm going to subtract the sum of the delta H of formation of my reactants from that. So I'm going to add up the delta H of formation for my products, I'm going to add up the delta H of formation for my reactants, and then I'm going to subtract my reactants from my products. And the only real trick is just make sure you notice your coefficients right in front, so your molar coefficients, because the molar coefficients have to be involved in your calculation. So I think the best way to learn it is to just do an example. Okay, so I move that table down a little bit. So our reactants, or sorry, our products, so remember you have to do the products first, are carbon dioxide and 2 water molecules. So we're going to come down here and we're going to look for carbon dioxide and our water molecules. And so let's see, CO2, where would we find that? All right, so here's our CO2 gas, and there's the enthalpy of formation for that. And then we're looking for water, H2O, and you'll notice that there are actually 2 waters, liquid and gas, and they have a different value, which would make sense because if you're going to form liquid water versus gas water, it's going to involve a different amount of energy because we're talking about 2 different phases. So we need to go look at our equation and figure out which we're dealing with. So hopefully were given states of matter, and it looks like we're dealing with liquid water here. So we're going to find the delta H of formation for liquid water instead of gaseous water. And it's negative 285.830, and remember here's the units, kilojoules per mole. So we're going to go up here and we're going to plug those numbers in. So we're going to take the sum of our products. So CO2 was negative 393.509. And we're going to add to that, and remember there was only 1 mole of carbon dioxide. We're going to add to that 2 times the enthalpy of formation for liquid water. And that is negative 285.830 per mole. And we're going to add that all up. And then we're going to subtract from that our enthalpies of formation for our reactants. So our reactants are methane gas, so CH4 gas, and 2 oxygen gas molecules. So let's go find those in our table. So methane gas right here is negative 74.81. And then oxygen, let's find O2. So I'm sure it's in here somewhere. Okay, you'll notice O2 gas has a 0, or an enthalpy of formation of 0. Now, you might be wondering, why is that? You'll notice there's a lot of things in here that have enthalpies of formation of 0. And the reason why that is because oxygen gas, that's the standard state of oxygen. That means that at room temperature, at 1 atmosphere, at 25 degrees Celsius, oxygen gas is the most stable form of oxygen, so its enthalpy of formation is going to be 0. You'll notice the same is true for F2 gas, H2 gas, CaCO3 solid at room temperature, you'll notice has an enthalpy of 0. So whenever we see a standard state of 0, or rather an enthalpy of formation of 0, that just tells you that at room temperature, at standard state, that's the most stable form of that compound. It's how it exists just naturally without any sort of intervention. Okay, so we're going to go back and we're going to plug in those numbers. Okay, so we're dealing with 1 methane, so negative 74.81. And of course, we're going to add that to our 2 oxygens, but they had a standard enthalpy of 0. So there you go. So at this point, it becomes just doing math. So we'll do this in pieces. So if I sum up my reactants, enthalpies of formation, I get negative 965.169. That's, of course, kilojoules per mole. And I'm going to subtract that negative 74.81. And what I get for my final answer is negative 890.359 kilojoules per mole. So there's my enthalpy of reaction at standard state, standard, one molar aqueous solutions, 1 atmosphere pressure, 25 degrees Celsius, for the combustion of methane. So, of course, the only way you're going to be able to do these kinds of problems is if you're given one of these tables, which you will be given, of course, one of these tables. And if you are not on a homework assignment, for example, this is one of your appendices in your textbook. You can find heat of formation values in your textbook in the back. Okay, so now let's talk about how to calculate the enthalpy of a reaction using bond energies. And again, you'll notice that we're talking at standard state here because of that little knot. We're talking standard states. So again, this is only going to work for calculating the enthalpy of a reaction if you're at 25 degrees Celsius, 1 atmosphere of pressure, and of course if we're talking about aqueous solutions, 1 molar aqueous solutions. Okay, so in order to make calculations using bond energies, of course you're going to need a table of bond energies. I want you to notice a few things before we do an example. So the first thing I want you to notice is that these average bond energies are all positive numbers. None of them are negative. The reason for that is because these bond energies are the amount of energy it would be required to actually break those bonds. And to break a chemical bond, you need to actually put energy into it. So it has to absorb energy to break it. So all bond energies are going to be an endothermic process because you have to add energy to break that bond. And the second thing that I want you to notice are that the bond energies are an average bond energy. So it says right at the top that it's an average bond energy. So what does that mean? Well, the way that they determine the bond energy, how much energy is required to break a bond, is they take a whole bunch of compounds that have these particular bonds in them and they measure the amount of energy required to break those bonds. And they find, for example, with OH, depending on what the compound is in, so depending on what else that oxygen is bonded to over here, that's going to affect how much energy it takes to break this OH bond. And so they just do this for a whole bunch of compounds, figure out the amount of energy to break that hydrogen off of that oxygen, and then they average them all together. So you just need to know that that's an average, that these are all average numbers. All right. So let's do an example. So here's an equation that I might ask you to calculate the delta H of reaction for using bond energies. Now, the trick to these is, I guess it's not really a trick, but you have to draw the Lewis dot diagrams for these elements, or these compounds, sorry, so that you can tell what bonds we're talking about. So don't ever assume that you know the bond until you've drawn a Lewis dot diagram. So the Lewis dot diagram for carbon monoxide which is right here, is this. So if you don't remember how to draw a Lewis dot diagram, you may want to Google instructions. I will see if I can dig up a video and post it along with this one that kind of walks you through how to do that. But there's some really good websites out there that'll tell you how to do it. And it's absolutely crucial that you know how to do this for this particular method of adding up an enthalpy of formation. And I don't know if you noticed, but there's two of them in your equation. So I'm just going to go ahead and put a parentheses and a 2 around it just so I can keep track of that. And then oxygen's Lewis dot structure looks like this. And there's just one oxygen in our equation. And then carbon dioxide looks like this. And of course, you'll notice there are 2 of them. So don't forget your coefficients. Okay, so now comes the fun equation. All right, here's the equation that you'll use. So you're going to take the bond energy for the bonds that are being broken. So that's essentially your reactants, right? Those are the ones that are going to have your bonds broken. And then you're going to subtract the sum of the bond energies of the bonds that are formed. And of course, that's going to be the bonds forming in your products. So we'll go do this by looking up bond energies in that little table above. So we're looking at, for our reactants anyway, we have carbon monoxide, and carbon monoxide just has a carbon and an oxygen with a triple bond. So we're going to look for that bond energy. It's 1070 kilojoules. Remember, we have 2 of those. So that means that we are going to have 2 1070s. And we're going to add to that, because we're taking the sum, our oxygen bond, because that's our other reactant right here. And an O2 bond is a double bond in oxygen. And you'll notice up here it tells you that O2 is 498, and there's just 1 of them. And we're going to subtract the sum of the bond energies for our products. In this reaction, our product is 2 carbon dioxide molecules. Each one contains 2 CO bonds. So this is where it gets really tricky. Yes, I have 2 carbon dioxides, but each carbon dioxide contains 2 double bonded, or carbon double bonded to oxygen bonds. So we actually have a total of 4 CO bonds, and you'll look up here and it tells you that in a CO bond in CO2 specifically is a bond energy of 799 kilojoules. And then if we do the sum of our reactants or the bonds broken, we get 2638. And we're going to subtract from that, of course, 4 times 799, which is 3196, and what we end up with total overall is negative 558 kilojoules. So this reaction, just from bond energies, should give us about 558 kilojoules of energy. Notice that it's negative, so what does that tell you? Hopefully you realize that that negative means that it's giving off energy. So this, of course, is an exothermic reaction. So there you go. I hope this helped.